Hey everybody, it's Mr. Carr again. Today we're going to be talking about 6.5 day one, and it's going to be operations with radical expressions. So the goal here is to simplify our expressions with a product property. What that means is, so when we look at this one, for example, we want to rewrite the radicand so each factor is raised to a power matching the index, same as before. And then simplify, same as before. Here's where things are a little different. When you look at this, b to the ninth is not a perfect square. So the product property of a radical says this: I could split this up as the square root of 25 a to the fourth, b to the eighth, times the square root of b. The reason why I did that is because now everything inside the first radical, I can write this as 5 times a squared times b to the fourth to the second power, and then times the square root of b. My reason for doing that is now I can cancel out that squared. So this is what's going to be on the outside. So 5a squared b to the fourth, and then times the square root of b. And that's it. Okay, so that's the change that we're doing in this case. So we're going to have this, whereas before we would have just ended up with this. Okay, so that's what our focus is. And this works for any of our radicals. So if I have the third root, again, I want things in terms of the perfect cubes or anything that has, like, in terms of the exponents, something that is a factor of, or a multiple of 3. So for example, I'm going to have the cube root 125 m to the 30th. I'm going to keep it as m to the 30th because that does work. And then p, 20 does not work. I cannot take 20 divided by 3 evenly, but I can do 18, which means I have the cube root of p squared left. Okay, so I'm just splitting them up into their own radicals, p to 18th and p squared. The reason why I would do that, because this I can take the cube root of. So now I'm going to take the cube root. 125 is 5 cubed, so I'll put a 5, m to the 10th, p to the 6th, to the third power, times the cube root of p squared. So now from there, I can cancel out that right here. I can cancel this out with this. So 5m to the 10th, p to the 6th, times the cube root of p squared. Okay, and that's it. That's what we're trying to do. So other examples of this one. This is one I'll let you try on your own. So another one there. Now let's look at when we deal with the quotient property. So apply the quotient property of radicals. And again, what that means is, just like with our multiplication or product property, we can split them up as two separate radicals. So it would be the square root of y to the 8th over the square root of x to the 7th. Rewrite the radicand so each factor is raised to a power matching the index. So again, in this case, y to the 8th does work. So I can make that the square root of y to the 4th to the second power. But underneath, it does not. X to the 7th does not have a perfect square. So instead, it'll be the square root of, well, let's do this a little bit differently. I'm going to split them up as 2 square roots. And I'll do x to the 6th and then the square root of x. Okay. From there, I'm going to leave it, so x to the 6th, scroll down a little bit. So I have the square root of y to the 4th to the second power. I can rewrite this as x to the 3rd to the second power, and then the square root of x. Simplifying these now, this turns into the y to the 4th over x to the 3rd times the square root of x. Okay, now the last step of this, I've done a lot of the same things I've done previously, but now with a fraction, rationalize if the radical remains in the denominator. To rationalize it, we're going to multiply by the square root of x to both the numerator and the denominator. Okay, so I want to do that because what happens here is x, the square root of x times the square root of x becomes an x. So my numerator is going to be y to the 4th times the square root of x. My denominator is going to be x to the 3rd times x. So one more thing to do is put those together. So y to the 4th times the square root of x over x to the 4th power. Okay, so that's how that one finalizes. Now you can take your own shortcuts here. I'm just showing the fact that first I want everything in terms of being raised to the second power. Then I can simplify those to these values and then rationalize the denominator if there's still a radical down there. Okay, so we'll do one more on this one. And now we're doing cube root. So again, we're going to split them up into 2 so that this is the quotient rule. Cube root of 9x. Now, when I look at this, there are no perfect cubes. 9 is 3 times 3. and 2 is almost just, it's prime, okay? And then x also does not have a perfect cube. So actually, I'm going to go right to rationalizing here. There's nothing else I can break down and simplify this, so I'm going to multiply by the cube root of 9x, cube root of 9x. Okay, so what happens here? Oh, actually, so multiplying by the cube root of 9x is not going to help in this case because it does not create a perfect cube. I'm still going to have a radical underneath. Good catch on that one. So instead, I'm going to do this. I want to figure out what does 9 times something gives me a perfect cube. Okay, so over here, 9 times something gives me something that I can take the perfect cube of. So if I think about, like, say, for example, 3 cubed, that's 27, which means 9 times 3 gives me that. Okay, so what I'm going to do is I'll multiply it by a 3 in here. X times x squared will give me a perfect cube there, right? Because x squared times x is going to be x to the third power. So that's what I'm going to do for my numerator and my denominator. So it gets weird because of the perfect cube that we're looking for. So my numerator, the cube root of, and using my product property, I can put these together. 2 times 3 is 6, and then x squared. In my denominator, I'm going to have now the cube root of 27x to the third. Okay, and again, the whole reason for that is this is a perfect cube. So I can rewrite that as the cube root of 6x squared over the cube root of 3x to the third power. And now I can cancel out that third power there. So I have the cube root of 6x squared all over 3x. And that's as simple as we can get with that problem. Okay, so again, it gets weird because of the cube root. We need to make sure that we are creating a perfect cube in my denominator when I do my rationalizing. Okay, all right, so that's a one you can try on your own. It's another one there. Multiplying radicals. So you kind of already see what I did there. Write all radicands under one radical symbol. Rewrite the radicand so each factor is raised to a power matching the index, and then simplify. So the product property works similar when I put them together instead of just separating. So for example, since these are both cube roots, I'm allowed to put them together under 1. So 5 times the cube root, this will be 100 times 10, a squared times a. Everything goes together under the 1, and I just could rearrange a little bit since it's all multiplication anyway. So 5 times the cube root, this will be 1,000 a to the third power. Okay, so 1,000 has a perfect cube because this is 10 to the third power. So 10 times 10 times 10 gives me 1,000. So if I can rewrite this then as 10a raised to third power, that's my step 2 here. Okay, from there, simplify it. So I have 5 times, it'll be just 10a, which means I can take 5 times 10 is 50a. So still applying the same rules we did, we just couldn't just put them together first under one radical. Okay, so you can check that one on your own. Adding and subtracting radicals. We're just going to simplify each term first, and then we add like terms, kind of like with like adding like terms with variables. Like if I can do 2x plus 4x gives me 6x. Okay, works the same way with square roots and radicals. It'll be 2 times the square root of 2 plus 4 times the square root of 2. I could put those together as 6 times the square root of 2. But notice they have to be the same. If I have 4x plus 3y, those do not go together. So that means if I have 4 times the square root of 2 plus 3 times the square root of 3, again, they do not go together. So when I add and subtract these, I'm going to start off by breaking them down. So 45, if I look for perfect squares, 45 is 9 times 5. So I can take the square root of 9 is 3. And I already have a 3 on the outside. So this is going to be 3 times the square root of 5. 80, look for the perfect squares there. That will be 16 times 5. So I take the square root of 16, that's a 4. So I'm going to have a minus 5 times 4 times the square root of 5. And the last one is 20, that's 4 times 5. So the square root of 4 is 2. So on the outside, I have a plus 4 times 2 times the square root of 5. Let's simplify the multiplication. So 3 times 3 gives me 9 root 5 minus 20 root 5 plus 8 root 5. So from there, it's just a matter of combining my like terms. I'm still going to have the square root of 5 as my final answer. but I got 9 minus 20 plus 8. So that's going to give me a -3 times the square root of 5. Okay. So again, the big part about adding subtracting radicals is they have to be like terms first. And like terms in this case means they're the same square roots. It also has to be square root versus cube root. So if we did, is that on? Nope. If we ever had one where we had square roots and cube roots, they cannot go together because they're different radicals. Okay. So you have to have the same index and radicand then. Okay. All right. And that's one for you to try on your own. And that is it for today. So lots of operations with our radical expressions. Combining like terms is a big part of it, but make sure you understand the multiplying and dividing with those and how to rationalize the denominator. All right. That's it for today. Take care.